Welcome. I'm Ingrid Hendy. I'm a professor at the Earth and Environmental Science Department at the University of Michigan. And I'm going to tell you today a little bit about how the drilling program that we've had in action since the 60s has changed the way we view planet Earth. Many things that it's done you probably didn't even know happened. So this is the history of the International Ocean Discovery Program as it is known today, but it's had a number of names through the years. It came about in the late 50s when a group of Earth scientists came up with a revolutionary idea. They were trying to think of a big project, and they thought, well, why don't we drill to the Moho? The Moho was a recently theorized discontinuity on the planet that separated the solid crust from the plastic mantle below. And it was key to understanding a new theory that had just been coming about called plate tectonics. Continental drift had been around since the beginning of the centuries, but geophysicists couldn't explain how the continents move through Earth's crust. And so even though there was a lot of evidence to support it, they had discounted it. But now as we come out of World War II, there are a lot of new technologies available, one of which is we now have an array of seismometers. And that is a result of international countries trying to work out who is testing nuclear bombs. These array of seismometers are also picking up earthquakes, and the earthquakes are traveling through the Earth and telling us something about the properties of the Earth below the surface where we can't see it. And so this big idea was, why don't we drill down and find these changes? Why don't we go down to the Mohorovic discontinuity, or for some reason, it's just gone forever as the Moho, and find out if this is actually true. So this also came out of some of the other changes from World War II. We have been measuring the bottom of the ocean since the 1920s using sonar, sound navigational ranging. But with the advent of submarine warfare during World War II, the number of sonar records that we had increased dramatically. And there was one person who was key in taking all these records and producing a map from them. So by the 1920s, we had enough sonar to know that there was some kind of large object in the middle of the Atlantic Ocean, but it took a woman known as Marie Tharp to actually map this out and show us what it is. Now, she, like many women in her time, in her day, was given very little choice of what she could study at university. So she did the arts, as many women in her time did. But by the end of World War II, there were a lack or a shortage of men in the program. And so although she did her undergraduate degree in arts in Ohio, she was actually from Ypsilanti, just down the road from where we are. And she got accepted. There was one place available for her in the geology master's program at the University of Michigan. And so she came and did her master's at Michigan. And after her master's, she looked for a job, and the only job she could find was in cartography, making maps. And so she went making maps. And by the late 50s, she was at Lamont Doherty Earth Observatory, which is part of Columbia University. So she couldn't go out on a ship. So she had a colleague, Bruce Hazen, who went out for her, and he collected all the sonar images and brought them back, and she mapped them up. And her map showed that the ocean floor was not flat like people had always imagined it had been, but there were canyons and ridges and mountains, just as impressive as what we find on land. So by 1952, Marie had found or had mapped out a MidAtlantic Ridge. And she was also putting in her mind with her friend Bruce, thinking about some of the new theories that were coming out surrounding this crazy hypothesis about plate tectonics. And one of those theories was that maybe there's a place on the seafloor where the ocean moves apart and we make new crusts. And so she thought maybe her new ridge that ran through the middle of the Atlantic was an area of seafloor spreading. And this seemed like a really good idea because if you looked at the ridge that she found, it mimics the shape of the continents on either side of it, of of Europe and North America and of South America and Africa. And so it was easy to imagine that these continents had drifted apart from each other as new seafloor had been made and pushed these continents apart. So in 1957, they promoted the idea of the Mid-Atlantic Rift Valley. So 1957, we've got these ideas coming together that maybe plate tectonics is true and we need to test it. And so what better way to test it than to go out and drill down through the solid crust to where the crust is plastic, moving or able to be moved, and we can move our continents around. Seems like a really great idea. They knew about the moho, or this supposed place where we went from solid crust to plastic crust because of the seismic waves, but they hadn't actually seen it. And so this seemed like a great test. It was also helped by the fact that there was a lot of competition at the time with the Soviet Union. Now, the Soviet Union in 1957 had launched Sputnik, so launched a satellite, and the US, America, was behind in the space race. And so there was a lot of competition, and this spurred a revolution in science and education, and it seemed like a really great time for an ambitious science program. In addition, the Russians, the Soviet Union, was also looking for the moho, but they had chosen to look for it on land, and they started a 10-year project to drill down to the moho. The US had a different idea. They said, we can't drill on land, we're going to drill in the ocean. And they came up with this idea of Project Moho, which in 1957, they got $2.5 million to begin. And they began phase one, which was an experimental drilling program to see if they could drill in the ocean. Phase two, they were going to get a vessel and start a drilling program. In phase three, they were going to drill to the moho. Okay, so what the US scientists did was they said to themselves, you know what? We can't drill through the crust. The crust is between 30 and 70 kilometers thick. 30 and 70 kilometers of drilling is a lot of drilling, which is sort of why the Soviet Union was at it for 10 years and they never got to the moho. The US were a little bit smarter, or a little bit more canny, and they thought, why don't we go to the ocean? The ocean crust is much thinner. It's on the order of 7 kilometers. And so we should be able to drill through this much quicker. Now, the problem was at this stage, we didn't know how to drill through to the ocean floor because the drilling that we had done, the oil drilling that we had done at this point, had all been from structures that were attached to the earth when they drilled. And to drill to the ocean floor, we want to get out beyond the shelves and out to where the ocean crust is. We would need to drill from a ship, and that ship would need to stay in place. And that was something we didn't know how to do in 1957. So they had to work out how you drill through the ocean floor without a drill rig attached to the seafloor. Up until this point, they'd done some offshore drilling by building little islands just offshore, but they couldn't get more than a few tens of meters, really. Okay, so now the oil companies were also interested in this because they wanted to get oil reserves that were offshore. And so they got on board and they put together a vessel known as the COESSING. The COESS stood for Continental Union Superior and Shell Oil. And it was a repurposed World War II lander. At that stage, coming out of World War II, there were a lot of extra military equipment around that was no longer in use. And they came up with this ingenious idea of putting a drill rig on it and keeping it in one location. This is known as dynamic positioning. And they figured they could do this by putting a series of buoys. So this is what they're lowering over the side of the ship here, a series of buoys around the ship. They would send out sonar to the buoys and they would know where they were relative to the buoys, and they would keep themselves in position using 4 very large outboard motors. So in terms of being very large, here is the outboard motor here, and it is off a jetty. So this is not going on a little runabout. This is a massive outboard motor. So they put an outboard motor on each side of the ship, and then they put the buoys around the ship. And the buoys told the ship exactly where it was. And some poor soul for the next month, it wasn't one poor soul, it was many poor souls, had to sit there with a joystick and keep those outboard motors going and keeping the ship over the same location. This was cutting edge. No one had done this before. And in fact, there was a lot of people who thought that they would fail. But instead, it was successful. And they managed to bring up rock from the seafloor. They were able to bring up some basalt from the seafloor and demonstrate that the seafloor indeed was made of basalt. They did this drilling off the coast of Baja, Mexico. So, and the other thing about the ship was it had no power of its own. It had these large outboard motors that could keep it in place, but it couldn't actually get to the site. It had to be towed to the site. It didn't have its own power. Okay, so they got a core that was about 160 meters in length, and these cores successfully confirmed that there was a basalt seafloor under sediments, and that the sediments sitting on top of the seafloor were Miocene of age. And so it was a big success, but phase 2 never happened. There were a number of things that happened in 1963 that proved fatal to the project. One was the human personalities. There were some very big egos involved. Another was the difference between the engineering goals and the scientific goals. There are a number of political improprieties at the government level, and there was also the complexity of managing such a large project that was escalating in cost, because it was set out, a group of scientists came up with it, but it turns out if you want to do something this massive, you need an entire management system, and they didn't have that in place. And so Congress in 1963 nixed phase 2. But they had realized that drilling was possible. And so Lamont Doherty got together with 3 other oceanographic institutes to come up with a ship that could do deep sea drilling. So Lamont Doherty got together with Scripps in San Diego and Woods Hole in Boston and University of Miami in Florida, and they formed JOIDES, which is still around today. JOIDES is the Joint Oceanographic Institute's deep earth sampling. And so in 1967, this is 4 years later, they began construction on a newly dedicated scientific drill ship known as the Glomar Challenger. And drilling began in 1978 and the ship operated for about 40 years, but it was only sustained by JOIDES for the first 5 to 7 years, after which it was realized that to maintain this, we needed to have international buy-in. And so Germany, France, the UK, Soviet Union joined in, and it became an international program. And as such, it is the longest running international program in earth sciences. Okay, almost immediately they had success because we didn't know what was on the seafloor. On the first leg, the second site they headed to demonstrated that there were actually salt domes in the Gulf of Mexico, and underneath those salt domes, there were oil reserves. And so that made the oil companies incredibly happy. Already success. But they started taking cores around the world. They took cores along the MidAtlantic Ridge between South America and Africa, and they were able to provide proof that the seafloor was being made, and that supported at the Mid-Atlantic Ridge, just as Marie Tharp had predicted, which strengthened the theory of plate tectonics. And then they demonstrated the ocean floor is relatively young. The Earth is 4.5 billion years old, and the oldest ocean floor they collected was 200 million years old. So the ocean floor is very young relative to the rest of the Earth, and so the ocean floor has to be being destroyed somewhere. The cores that they pulled up demonstrated the relationship between the age of the crust, Earth's crust, and Earth's magnetic reversals. They were able to show that Earth's magnetic reversals were being recorded in the crust in the way that was theorized by Vine and Matthews. And they began to show that the chemistry of the ocean has varied greatly through time. It's impacted the type of sediments that was deposited on the seafloor, and that was the result of changes in the tectonic position of continents and climate. So dating of the seafloor, they were able to demonstrate that the youngest seafloor is occurring at the mid-ocean ridges. And the oldest seafloor is as far away as you can get from the mid-ocean ridges in that ocean. And so the Atlantic Ocean has been opening fairly slowly. So you see the oldest material out off North Africa and off the east coast of the US. In the Pacific Ocean, there has been a lot of subduction. And so a lot of the oldest material has been subducted back under North America. But if you go over towards Japan, you'll find very old seafloor there. And so the relationship between the age of the seafloor and how far away you are from where new seafloor is being formed demonstrated that indeed the way to move the continents around is by seafloor spreading. Another major find, and this is actually a compilation of data from the programs that followed the first program, which was known as the Deep Sea Drilling Program, was that the Earth's climate has changed dramatically over this time period. And notably, over the last 50 million years, the Earth's climate has cooled dramatically from a climate where we had palm trees and crocodiles up around the Arctic to a climate where we have permanent ice over Greenland and over Antarctica. At the same time, we have seen the ocean basins change their shape, and then gateways, which are regions where water can move from one ocean basin to another one, have opened and closed. So this is a temperature estimate based on the ocean isotopes of microfossils. These are replicas of microfossils. This is a surface-dwelling foraminifera known as Globigerina beloides. And this is a 3D model. This would be the size of a grain of sand, but it makes this shell out of calcium carbonate, and we can use the oxygen isotopes in that calcium carbonate to estimate ice volume and temperature. So this is a surface dweller. I have a deep dweller from the tropics. The previous one was a cosmopolitan species that lives in upwelling regions. This is a deep dweller from the tropics. And then you can also have foraminifera that live on the seafloor. And so this is a benthic foraminifera known as Cibisidoides wollenstorfi. And with the benthic ones, the guys living on the seafloor, you can tell something about the temperature and the oxygen isotopes of deep waters. So this is a compilation of many, many cores taken over many, many years. And we can see from 50 million years ago towards the present that we've seen cooling on the planet. During this time period, we have had gateways open, like the Drake Passage between Antarctica and South America, and the Tasman Gateway between Antarctica and Australia have opened up, and that's provided us the Southern Ocean and begun the isolation of the Antarctic continent. And so Antarctica has seen saw the early development of ice sheets. We have uplift of the Tibetan Plateau, providing a draw of CO2 out of the atmosphere. But we also have a change in ocean circulation when we change other gateways, like the closing of the Central American Seaway between North and South America, and the closure of the Tethys Ocean to give us the Mediterranean. As the planet's cooled, we've seen an increase in the aridity of the planet as well. So the ocean drilling program provided us this history of the Cenozoic that we didn't have before. This is in part because through the deep sea drilling program and then the later programs, the ocean drilling program and the integrated ocean drilling program and the international discovery program, we've continued to have innovations in the way we collect cores. And one of these innovations is something known as piston coring. Piston coring is basically where you take a core of the sediment, you shove a long pipe into the sediment, and then you have something like a syringe that sucks the sediment up into the pipe, and that allows you to get high quality, high resolution sediment samples, soft sediment samples. And with these records, we've been able to create detailed accounts of past climate change or past changes in the ocean environment from annual scales through to tens to hundreds of thousands of years. And within that, we've been able to identify orbital cycles, and that lead to the repeated cycles of polar ice sheet growth and collapse, and the large sea level fluctuations of up to 120 meters on the planet. So I showed you the 50 million year cooling through the Cenozoic and the development of the Antarctic ice sheet and the Northern Hemisphere ice sheets. If we look at the last 5 million years of that, so this is the last 5 million years, you can see the cooling, but you can also start seeing these orbital cycles. And these orbital cycles are relatively small through to about 1 million years ago. And they're also dominated by a 40,000 year cycle. And then around about 1 million years ago, well, actually 500,000 years ago, we go into what we call the 100,000 year world, where now the growth and retreat of the ice sheet is paced at 100,000 years. And so this is the 100,000 year world here. This is the warm time period we live in right now. This is the last time that we had a kilometer of ice sitting above me in Michigan. And then this here at about 120,000 years ago was when we last had a time period like today. And so without the drilling program, we would never have worked out these cycles. Prior to the drilling program, we thought there were only 4 cycles, only 4 ice ages. And that was because we could only see the last 4 major warmings or the last 4 major coolings in the ice on records on land. And so we discovered that there have been hundreds of ice advances and ice retreats over the last few million years. And with these cores, we're able to reconstruct everything from sea surface temperatures, bottom water temperatures, presence of sea ice, history of ice sheets, CO2 concentration in the atmosphere, the productivity changes in when we're drawing CO2 out of the atmosphere and putting in sediments. And that's just the climate part of the record, because the drilling program doesn't just do climate, it also does seismology and hydrology and numerous other deep sea science questions that are associated with a drilling ship. Okay, so the orbital cycles, we would never have been able to guess without the drilling program. The orbital cycles are changes in the Earth's orbit around the sun, and they're responsible for the amount of solar radiation we get, both the total amount and the amount we get on certain seasons. And so the total amount of radiation is controlled by eccentricity. Eccentricity is the shape of the Earth's orbit. It goes from circular to elliptical. And the sun is not in the middle of that orbit. It's off to one side of that orbit. And so one side of the orbit, the Earth moves far away from the sun, and the other side of the orbit, it's close to the sun. And there are 100,000 year and 400,000 year cycles within that. And so that's controlling the total amount of solar radiation. But the degree of seasonality, how strong our seasons are, depends on the tilt of the planet. And the tilt of the planet varies between about 21 and 24, 25 degrees. Right now, we're around 23 degrees. And the cycle of that tilt, or the maximum minimum tilt, is 40,000 years. And that's our 40,000 year world. And then we have one more thing, which we call precession. It has around a 20,000 year cycle. Rather, there's a 19 and a 23. So if you average that together, you get 20,000 years precession. And that changes the amount of solar radiation we have in different seasons. So you can have warmer summers in the Northern Hemisphere or colder summers in the Northern Hemisphere. And precession is the combination of the axis of rotation, which wobbles as the Earth travels around the sun, and eccentricity. So we like to think of precession like a wobbling top. If you set a top spinning, eventually it'll start wobbling, and that's kind of what precession is. Okay, so where this becomes important for climate is that when we are in conditions where the Northern Hemisphere summer, so the Northern Hemisphere is tilted towards the sun during summer, is at the farthest point away from the sun, we have a cold Northern Hemisphere summer. And because the Northern Hemisphere has the large amount of land mass, the cold summers allow that land mass to hold on to the winter snows and allow the ice sheets to grow. When we go into ice and melt conditions, we have a close Northern Hemisphere summer. And so that makes for a very warm summer, and we melt all our winter ice. And so the ice will start retreating. And so this is how the Earth's orbit is controlling our climate going into and out of ice ages. But our whole planet has been in a steady decline since 50 million years ago, and that has been driven by the amount of CO2 in the atmosphere. As we've lowered CO2 from around 1,000 ppmv through to what we were before the Industrial Revolution, 270 ppmv, we have gone from a world where we have palm trees and crocodiles in the Arctic to a world where we have a permafrost, permanent frozen ground in the Arctic. Okay, so the Glomar Challenger operated from running 68 to 1983, about 40 years. A ship lifespan is around 50 years. After that time, everything falls apart. And in that time, it had, if you took the total distance, it had penetrated below the seafloor. It's 325,000 meters. It recovered almost 100,000 meters of total core, which is about 57% of what material it drilled. That was 624 sites, over 1,000 holes, almost 100 expeditions. The deepest it managed to penetrate was 1.7 kilometers. And remember, the Moho is 7 kilometers down. So we're nowhere near the Moho. And the maximum penetration to basaltic crust was 1 kilometer. The deepest site it drilled was at 7 kilometers, and it traveled 375,000 nautical miles, which is multiple times around the circumference of the planet. Okay. By the 80s, though, we needed a new ship. And so the ocean drilling program, which was a joint effort between Australia, Germany, France, Japan, UK, in Europe, the European Consortium for Ocean Drilling began, built a ship called the JOIDES Resolution in 1985. ODP was succeeded by the Integrated Ocean Drilling Program in 2004, and then currently it is under the International Ocean Discovery Program in 2013. There's been a little change in the member countries coming and going, but together this makes it the longest running successful international earth science collaboration. And so this was me last January on the JOIDES. I was south of New Zealand, about 53 degrees south. This is where at this point we're laying down drill string at our site. And so it's very exciting. It was also a very nice day for the southern hemisphere at 53 degrees south. Still chilly though. We're in summer, still chilly. The JOIDES Resolution is a purpose-built ship. It's got a derrick, which stands about 62 meters above the waterline. The derrick is what does the drilling. It drops a drill string or a drill pipe from the ship down to the seafloor, and it can drop that down 7 kilometers, the deepest. On this particular cruise, we were meant to be going down 5 kilometers, but the ship broke, so we could only do less than 2 kilometers. But still, 2 kilometers of pipe from the bottom of this ship is impressive. The ship has dynamic positioning, and so instead of large outdoor motors, it's actually got thrusters, massive thrusters, 6 of them on the ship that hold it in place. It also has an ability to reduce the swell, and so we can drill into up to 15 feet of swell or waves. Above that, you kind of start bobbing out of the water, so you'd have to stop drilling, but 15 meters is still bigger waves than you really are comfortable in, so at least I'm comfortable in, so that's great. And so you drop this drill pipe down to the seafloor, and then you run your drill string through that pipe, up and down, and you drill. And what you drill, how you drill, depends on the type of rock you're entering. So there are different types of drill bits for different cores. When you're working with soft sediments, you're using a hydraulic piston core device, but they have a cutting device on the end of that when you start getting out of soft sediment. These guys down here are core catches, which are basically things that you stick in the bottom of the core to stop your core falling out as you pull it back up the drill pipe. So I have a old rotary coring device from the JOIDES Resolution. This one reached its end of use. If you can look closely, you can see there's a lot of damage to the teeth on this. And so this would have been dull, would have stopped recovering good core. On our ship, one of these actually totally disintegrated, and then we had to go and look for these little metal bits that were stuck somewhere in our core, but we have X-ray on board, so that wasn't too difficult. But that gives you an idea of the diameter of the core material that you're bringing up. Now, once you get through soft sediment, then you have to start actually drilling and drilling rock. And so that's what these things are here. These are for drilling through rock. And so on our cruise, after I would say close to 300 meters down was where we started to enter limestone. Our chalk started turning to limestone, and then eventually we entered mudstone, and we had to use drilling bits. And so these drilling bits go round and round and round, and they cut a circle rock in the middle, and that's what ends up in your core. And so I was lucky enough to get one of them. So this is it right here. This is one of the drill bits that you would see. And it's heavy. This is a good 10 pounds of titanium right here. It was fun trying to get this back through airport security. They did not really appreciate what this awesome knobbly thing was that had been down hundreds of meters below the seafloor in the Southern Ocean. I'll just stop the share so you can get a big view of it. So here we are right here. Oh, it's really heavy. I guess I'm making lots of sounds that make it, but it goes round and round. And these are the drill bits. So these are the bits that would have wrapped. And there would have been 4 of these in a circle for the core. And then this is the rotary coring device that you would put to go through sediments that are a little too tough for the hydraulic piston core. So this would be like chalk-like sediments. Yep. It's blurring out, but we can look at the damage on this. This one's clearly past its use by date. So there's damage on those teeth from use. Okay, so what are some of the records that we've got from this program? Well, one of them, one famous one is the KT boundary. So this is the KT boundary, not too far from the actual Chicxulub crater, which the ocean drilling program has actually drilled through. But this particular one is showing the impact of the meteorite impact at the KT boundary. And so you have normal Cretaceous sediment down here, everyone's happy. And then we have a really bad day on Earth where we have a layer of glassy globules of rock material that have been heated up and then splattered across the ocean, heated up by that impact and then splattered across the ocean. At the top of that, we get fallout. So this is a lot of like dust and ash from fires. And then directly above that, we find that there are very few microorganisms in the sediment. And so there's a time period where there's an empty sea, about 100,000 years, where there's an empty sea around this region that's been so severely impacted. And then new life evolves from the survivors. And after 100,000 years or so, we come back to sort of a new normal. And so it's really dramatic support for the longstanding theory that there was an impact at the KT boundary. And that was a reason for a widespread extinction and perhaps the final demise of the dinosaurs. And so drilling multiple holes around this region in 97, ODP Lake 171 recovered 3 cores containing these layers. Okay, there is some African stories, which you will hear one about the Argylis current from Sydney Hemming later in a synchronous lecture. But one that is famous is the evolution of humans and the change of climate on Africa. And so this is a 5 million year record. And remember, this is where we go from a 40,000 year world into a 100,000 year world. And as the planet continues to cool, we go from 40,000 year ice ages to massive 100,000 year ice ages. And we see an increase in diversity of hominids as we go into this 40,000 year world right here. And then they appear to have disappeared by the time we get to the 100,000 year world. What was happening on Africa was that we were seeing the development of a monsoonal climate where the amount of moisture in Africa and North Africa was changing dramatically. So there were time periods when there was a lot of moisture and hippos and other aquatic animals advanced into the Sahara Desert, and then it dried back up again. But as we move closer and closer towards the present, we see more and more of this drying, and so more and more of grasslands and less of forests and less of these big aquatic time periods. And that seems to have an impact on the diversity and then the final survival of hominid species. I'm going to throw my PhD thesis in here, which was that the ocean drilling program was able to drill a few hundred meters in a basin off of California, which is has low oxygen in it today. And they were able to show, they thought it was going to be a record, annual record almost, of low oxygen, but we were able to show that actually off California, we had massive changes in the environment during the last glacial, where we went from a very a climate like today with a low oxygen basin that was warm to a climate where there was lots of oxygen in the basin and it was cold. And these changes in climate took place very rapidly. And so what you're looking at here are 4 to 6 degree Celsius temperature changes in intervals as short as 50 to 70 years. And we were able to show that these were exactly the same things that were happening in the Greenland ice sheet, meaning that the large changes in the Greenland ice sheet, which people thought were fairly regional, were actually happening across the northern hemisphere and were having a big impact, and that our climate was nowhere near as stable as we thought it was. Prior to this, we thought that it took thousands of years to melt an ice sheet, thousands of years to change temperature. But this showed us that no, in a human lifespan, we can dramatically change the environment in such a way that we have a complete change in the species present. There's also evidence for some greenhouse gas over warming at the beginning of these warming events. Okay, another, as we're moving forward in time, we're now moving into the integrated ocean drilling program. Another important core or discovery was the Paleocene thermal maximum. So this is 50 million years ago. This is the warmest time period, but the warmest time period is actually associated with a runaway greenhouse world, where we have the normal Paleocene ooze back here, and then close to the transition from the Paleocene to the Eocene, we have a very rapid onset of warming. And this warming was caused by a larger release of greenhouse gases, of which CO2 had to be a large component because it changed the chemistry of the ocean. It made the ocean very acidic, and that ended up dissolving all our microfossils. So remember these guys? Well, they are down here in this whiter stuff. And then when you get into this red stuff, they've all dissolved out because the ocean became acidic. And the climate warmed very dramatically. We had some really crazy animals, like the horses got to the size of small dogs. There's some really amazing changes in the species on the planet in response to this rapid warming. And a very large change in the ocean chemistry as a result. Yeah, and as I said before, it's not just about climate. Climate is what I do, so I'm fascinated by the climate questions, but there's some other questions. This is a deep basalt core that would have been drilled with one of these coring devices. And this is in the East Pacific Rise. They drilled one of the super fast spreading areas where it was spreading at the rate of 200 millimeters, 20 centimeters a year. 20 centimeters a year is massive. When we normally teach about seafloor spreading, I say it's grows about the speed of your fingernails. 20 centimeters a year is massive. And this is the transition from the upper ocean oceanic crust to the lower oceanic crust. So the upper oceanic crust has basalts and dikes in it, and the lower oceanic crust has gabbros, and it's around about 1.5 kilometers below the sea floor, the actual ocean crust. And so what they were trying to do here was they're trying to understand how the lithology of the sediment changed and relate that back to seismic velocity. So remember, our earthquakes produce seismic waves, and they travel through different rock densities, and they tell us something about those rock densities because they slow down or speed up depending on the rock density. And so they were actually sort of ground truthing what those rocks are, because we don't know. Obviously, the ones that are very deep below the crust, we don't actually know what they are. So the ocean drilling program was able to go down 1.5 kilometers into the ocean crust to demonstrate what those changes in seismic velocities were. And as we move forward in time, we also start getting different types of drilling programs. So the International Drilling Ocean Discovery Program actually has different types of platforms. It's not just the JR, the JOIDES Resolution, the ship I sailed on anymore. We have a Japanese ship known as the Chikyu. It's a massive drill ship. And we also have site specific. Sometimes you don't need a drill ship. You do need to do ocean drilling, but a drill ship is not quite what you need. So the Chikyu in 2012 drilled through the plate boundary that was associated with the Tohoku earthquake of 2011. What you're looking at here is the actual plate boundary, and you can see within this plate boundary you've got lots of shiny brown clay that's deformed, and it's this scaly fabric that allows the plate boundary fault to actually move the way it does. And so drilling through this provided information about what the rock material, the rock fabric was like, that can give you some estimate of how much pressure and how much you can actually deform that rock before it will rupture. And then the final one I'm going to talk about is a drilling through the coral reef off Tahiti. Again, this was another mission-specific platform. They didn't use the JR. And what they were doing here was they were drilling through the reef terraces to look at where the reefs were during the last ice age when the sea level was 120 meters lower. And so what you're looking right now is a section of massive coral called Porites. Porites is a deeper dwelling coral. It is 14,500 years old. And so there's the Porites right there. And below that is some microbialite crusts, another Porites down here. Above it, you end up with time period when the coral was not very happy. And so you start getting algae growing on it and gastropods, and then it dies. And then you start getting mud on top of that. And this is where sea level was 14,500 years ago. And it's showing these series of cores showed what the sea level rise was after the last ice age. And so how quickly did the ice sheets melt? How quickly did sea level rise and flood this landscape, or send these poor corals down to the deep ocean below the photic zone where they couldn't survive anymore and they died? So we have had a very successful scientific drilling program since the late 1960s. The JR took over in 85, and in that time, it's conducted over 111 expeditions, drilled 669 sites. Then we move into the integrated drilling program. The JR has conducted 35 expeditions and drilled 45 145 sites, and currently we're in the International Ocean Discovery Program, still IODP. And as of 2018, completed 19 expeditions. And so you can see that core recovery has gone up dramatically over time. We've got better and better at coring. And we've started to break some of the rules, or some of the records. At this point, the JR has traveled almost 540,000 miles, nautical miles, visited almost 1,000 sites, drilled almost 2,500 holes. It's 51,000 cores, and 161 expeditions. And some of the other sort of statistics, the most northern site it's drilled at is 67 degrees north up in the Arctic. They're trying to get up to the Arctic right now. It requires multiple countries to bring their icebreakers on board to keep the ice away, because you don't want ice coming in and cracking the ship. So that's been a big effort to get the large number of icebreakers you need to support the ship. But it's hopefully, knock on wood, going back to the Arctic again. So the last time it was in the Arctic, they thought they would be able to tell us something about the Arctic Ocean opening up. And what they discovered was there was a time period when the Arctic Ocean was almost a giant lake. And so that was a pretty exciting find. You never quite know. You've got some idea of what you're going to look at, but you never quite know until you actually get there. So actually, the most northern site in the ocean drilling program was 80 degrees north. The most southern site, 70.8 degrees south. The shallowest water, 40 meters. And the deepest water depth, 6 kilometers. And the longest hole they've drilled was 2 kilometers, 2 kilometers of sediment. Okay, so that concludes what I was going to talk about. I will be around for the asynchronous event with Sydney Hemming and Laurel Childress, who is a technician for the ocean drilling program, or the International Ocean Discovery Program. She works at Texas A&M at the repository there, and she's hopefully going to tell us something about the storing of cores. What happens to these masses of amounts of cores that we collect, and what are your opportunities to get hold of some of those sediments and do some work on them? So I hope to see you at the synchronous event later in the month.